Welcome to this video on designing chaos experiments. In this video, you will learn how to design and execute effective chaos experiments to improve system resilience. By understanding the life cycle of a chaos experiment and the key considerations for safety and measurement, you will gain the confidence to apply chaos engineering principles to your systems. What is chaos experiments? Chaos experiments are controlled tests that introduce disruptions into a system to evaluate its resilience and behavior under failure conditions. These experiments help identify weaknesses, improve fault tolerance, and ensure the system can withstand unexpected challenges. Life cycle of a chaos experiment. Chaos experiments follow a structured life cycle to ensure their effectiveness. 1. Hypothesis. Hypotheses define what you expect the system behavior to be under failure conditions. Example, if the database experiences latency, the system will fall back to the cache and maintain response times under 200 milliseconds. This helps to clearly articulate the expected outcomes to focus the experiment and measure results accurately. 2. Execution. Execution introduces controlled chaos into the system, such as increasing CPU usage or delaying network traffic. Tools like Chaos Monkey, Litmus, or Gremlin are used for automation. This ensures the test environment is prepared and all stakeholders are informed before initiating the experiment. 3. Observation. Observation monitors system behavior during the experiment. This captures metrics such as response time, error rates, and system throughput. Using dashboards or observability tools like Prometheus, Grafana, or Datadog to visualize data in real time. 4. Analysis. Analysis is the process of evaluating the results against your hypothesis, identifying improvements to system design or response mechanisms, sharing findings in a postmortem document to inform future experiments and improve processes. Defining failure scenarios. Failure scenarios simulate real-world issues to test system resilience. Common scenarios include 1. CPU spikes. A process where one overloads the CPU to simulate high computational demand, and measure how other services are impacted. For example, one can simulate a spike to 90% CPU usage and observe service degradation or recovery mechanisms. 2. Memory exhaustion. Memory exhaustion is a process of allocating memory until the system approaches its limit. To check if out-of-memory (OOM) errors occur or services degrade gracefully. An example is when one gradually consumes available memory in a microservice to validate its resource management. 3. Network delays. Network delays is a process of introducing latency to mimic slow network connections. Observe how distributed systems handle delayed communication. An example is when one added 200 milliseconds delay to simulate poor network connectivity in a specific region. 4. Disk space shortage. This simulates a scenario where disk space is filled up by logs or temporary files. This is done to assess the system's ability to handle or alert such conditions. 5. Service downtime. This is a process of bringing down critical services or dependencies to measure the time to recovery and the impact on user experience. Establishing metrics to measure success. Metrics help quantify the impact of chaos experiments and guide improvements. Key metrics include 1. Response time. This process measures the time taken for the system to respond to requests. Ensure it stays within acceptable limits under stress. Use percentile metrics, for example, P95, P99, for granular insights. 2. Error rate. This is a process that tracks the number of failed requests or error responses. Look for spikes during failure scenarios. Compare error rates before, during, and after the experiment, to assess recovery. 3. System throughput. a process that measures the volume of requests the system can handle per unit time. Assess how throughput is affected by failures. Example, validate that throughput degradation is minimal under stress. 4. Recovery time. A process that measures how long it takes for the system to return to normal operations. Identify bottlenecks or inefficiencies in recovery processes. 5. User impact. A process of analyzing metrics related to user experience, such as session times, drop-offs, or satisfaction scores. Safety-first approach. Safety is paramount when conducting chaos experiments. And the following principles helps to minimize risk. 1. Blast radius control. This limits the scope of the experiment to reduce potential damage. Example, run test only on staging environments or a subset of production servers. Using feature flags or config. 2. Rollback strategies. A process of planning how to revert the system to its original state if the experiment causes critical issues. Using automation to ensure quick and reliable rollback. An example is implementing automated scripts to reset resource allocations or remove injected faults. 3. Stakeholder communication. This is a process of informing teams about the experiment, its scope, and expected outcomes. To ensure key personnel are on standby in case of unexpected issues. 4. Pre-experiment validation. A process of testing the chaos scenario in a sandbox or staging environment before applying it to production. Validating monitoring tools and alerting mechanisms to ensure readiness. In conclusion, designing chaos experiments requires careful planning, execution, and analysis. By following the structured life cycle, defining relevant failure scenarios, establishing metrics, and prioritizing safety, you can build resilient systems capable of withstanding unexpected disruptions. Remember, chaos engineering is an iterative process. Start small, learn from each experiment, and gradually expand the scope as your confidence grows. Please click the link in the description to access this lesson on Motiva Logic Academy Learning Management System, where you'll find a quiz for every lesson, hands-on lab and projects to test and strengthen your understanding. While you're there, explore the full catalog of advanced hands-on courses and downloadable resources designed to help you move from theory to real-world expertise faster. Be sure to like, subscribe, share and visit the link in the description. Don't forget to turn on notifications so you don't miss the future lessons. Thank you for watching.